Good evening, ladies and gentlemen. Welcome to Lecture 7 of Topic 2 of Unit 4, Blackbody Radiation. This video will be covering the main ideas of Chapter 11.2 of Book 2. Please complete this reading before class. Here are your learning intention and success criteria for the chapter. Please pause the video and attempt to complete the KS table down the bottom right corner there. Okay, so we have a sentence there that we need to explain a concept called blackbody radiation. We know what radiation is, it's type light, but what is blackbody radiation? And then there's this new thing here, identify how it provides evidence for the quantization of light. In terms of our success criteria, we have a few things there. We need to explain blackbody radiation, we need to calculate peak wavelength, and then identify the blackbody evidence. So for knowledge, what is blackbody radiation? What is quantization of light? If we don't know what this word is, it's very hard to identify some evidence for it. And then, well, what is the evidence? In terms of the skills, that calculate verb, can I calculate the peak wavelength? Pretty straightforward one in that case. So, what is a blackbody? All the objects around us constantly interact with light, everything you see. As said before in the topic, we see objects because they reflect light. Some objects we can see because they emit their own light, like my tablet screen here. Everything will also absorb light that hits them, which is why you get warmer standing in the sun. You absorb the light hitting you. And so everyday objects do a combination of these three things. Even, the light striking this camera, some of it's getting absorbed as heat because it's hitting the plastic around it, and some of it's hitting the photo sensor there. In that case, it's all being absorbed and being transmitted through the electrical signal. But everything is doing these three things. Now, in physics, a black body, which is not actually black, so most of the time the best black bodies look white when you look at them, and conversely the best white bodies look black, but we don't deal with white bodies in this in this topic. They only do two of these things. They absorb light and they emit light. Now, all light that strikes it is absorbed, okay? And that means it increases its temperature because light is energy, and if you absorb more energy you get hotter, okay? And then it gives off that heat as a glow, as its own light. The best example that we have really in nature for a black body is a star. Energy from any other star that hits it is most likely to be absorbed by the gases inside of it, by the plasma, and then given back off as light itself. But really not all much light actually hits it, so it's all about just emission in this case. Now, there was a German scientist by the name of Wien. It's German, so therefore the W is pronounced with a V. If you pronounce it Wien in your head, it really doesn't matter. No one's going to get you to pronounce these things. So I'll probably half say Wien and half say Wien through this unit. He grew up at a farm, and he would observe the blacksmith shaping horses' shoes as a young boy, because that's what you do when you're a kid growing up on the farm. You find the most dangerous, interesting thing, and that's normally the blacksmith. Now, as you probably recall from your junior grades, when you have a gorse mat over a Bunsen burner, they go from their metal grey colour to a dark red, bright orange, yellow, and if you heat it up long enough and the teacher doesn't catch you, eventually it goes white. And Wien worked out the relationship between wavelength of the light being given off and the temperature of an object, and this is the formula. Now, one thing that's really important to note is this T. It is not a change in temperature, it is an absolute temperature. So you must use temperature in Kelvin. Some of the other formula we've seen involving temperature, like Q equals MCAT earlier this year, that use changed in temperature, and change in Celsius is the same as change in temperature in Kelvin. So it was okay if you used Celsius, you didn't have to convert it first. But this one, you have to use it, because if you put in something like negative 30 degrees, well, you're going to get a negative wavelength, which doesn't make any sense. Okay? And the number would be also very, very wrong as well. So please make sure that you are, for this one, because there's just a T, it's not a delta T, it's not a change in temperature, you must use Kelvin. And the other clue should really be that you can't have a negative thing, negative wavelength. But if you've got something like, I don't know, 16 degrees Celsius and you chuck 16 into it, you're going to get the wrong thing. One thing I would suggest, if you're given a question like this where your temperature's in Celsius, show that you've converted it to Kelvin. Like, do the actual TK equals TC plus 273. Remember that formula is given to you as well, so you don't have to memorize how to convert, just remember to convert. So let's have a look at some examples. So we have here, calculate the peak wavelength for radiation from the Sun and Earth, given that the effective peak wavelength radiation, effective surface temperature of the Sun is 5800 Kelvin and the Earth is 16 degrees Celsius. And we want to identify the spectral regions for each of those wavelengths. So we're just going to describe them. So let's start off with math bit first. Yep. So we have here temperature of the Sun equals 5,800 Kelvin, and the temperature of the Earth, that might be shaking a little bit, equals 16 degrees Celsius. Just move that just a little bit, because it seems to be banging under my monitor. Now we need to convert. I'm going to do my conversions first for that. So remember, that means in Kelvin it will be 16 plus 273, which will give us 289 Kelvin. Okay, so if you're given something like this, do the conversion straight away. We're after peak wavelength. We're just using a very simple formula. Sometimes it's called wavelength peak. Other times you see it as wavelength max. Other times you just see it as wavelength. It doesn't matter which. B divided by T. B is a constant, which is 2.898 times 10 to the negative 3, divided by, let's do our Sun first, 5800, and that means our wavelength is going to equal 5.00 times 10 to the negative 7 meters. We'll convert that in a second. And the other one we have 2.898 times 10 to the negative 3 divided by 289, and so our wavelength will equal 1.00 times 10 to the negative 5 meters. So there's part A. Okay, that's all you have to do for part A. Part B, though, is asking you to work out the spectral region. What, like, is it a color? Is it infrared? Is it gamma? That sort of stuff. You would not be told that that's what spectral region means. You're sort of expected to know it. And remember, when we talked about light and certain wavelengths a while back now, I think in topic 3, unit 3, I did mention that it's probably worthwhile remembering just a few rough areas, because if you look in your formula booklet, there's no light spectrum provided for you. So I always like to convert it to nanometers. So this is 5 times 10 to the negative 7, which is the same thing as 500 times 10 to the negative 9 meters. Oops. Which equals 500 nanometers. 550, 540 nanometers is green, 470 is blue, so it's going to be blue-green. So for B, the Sun's peak is approximately blue-green. Okay. Now, the peak for the Earth, well, this is going to be 10,000 nanometers. Which is way past that point there. We could also represent as micrometers, because this would be 100 times 10 to the negative 5 is the same thing as 10 times 10 to the negative 6, which equals 10 micrometers. It also equals 10,000 times 10 to the negative 9, which equals 10,000 nanometers. Now, once you get past roughly 770 nanometers, you've got a big chunk of infrared. And the only thing below infrared is around the radio sort of area. The good news is that when we're talking about temperature and stuff, there's nothing really below infrared. So if it's bigger than, go 770, 800 nanometers, just say it's infrared. Don't overstress about it. It's the ones underneath ultraviolet, so underneath roughly the 440-ish through 400-ish nanometer range, where you start hitting in the ultraviolet. I would be very, very surprised if they ever gave you a question like this, where they asked you to work out something like something with a deep gamma ray, gamma waves, type of peak wavelength. I don't think anything like that could physically exist. I'm sure there's probably a temperature that does it, but it would have to be a very, very hot temperature. So it could be something you could work out, but it's more likely to be things in the UV through to infrared radius. Okay, so don't overstress it. Make sure it's lined up okay. Yeah. Okay. So now that we know how to work out the maximum wavelength coming off of our hot object, let's have a look at something else. Let's look at intensity and distribution. Now, when we look at a glowing object, we see a primary color, and that was Wien's law that we just practiced with. But light comes in other wavelengths too. It's just not as bright. If we graph that out, the intensity, the brightness versus wavelength, we get shapes like the following. Now here we have a few different temperatures. You see they've all got roughly the same similar shape. As the wavelength increases, it spikes up and then drops off. Spikes up, drops off, spikes up, drops off. It can help in this case to think about coming from this side, that as wavelength decreases, we see it spike and then drops off very sharply, because the other way this graph is often drawn is using frequency. And remember, frequency is inverse of wavelength, or at least related to the inverse of the wavelength, and so this shape gets flipped around a little bit. And frequency is going to be important when we talk about energy of light in a couple of lessons. The cooler objects we see are not as bright as hotter objects. Okay, so here's my 7,000 Kelvin, my 6,000 Kelvin. We can see its intensity is more than half that. You don't need to really know a relationship between you don't really need to know a relationship between it, but it's worthwhile being able to look at a graph like this and go, yep, as things get colder, the intensity drops off, so they're not as bright, which sort of makes sense when you think about your day-to-day life. The Gauss map, when it's not glowing red hot, is obviously not glowing red bright color. It's not as hot as when it's is glowing red hot, okay, so to speak. If you have a light bulb and the light bulb has not been glowing at all, it's cool. If it starts glowing and then you touch it, it's probably going to be quite warm, so you don't touch a hot light bulb, or a light bulb that has just been on. Brighter things are hotter, or hotter things are brighter, I should say. As with Wien's law, okay, like we just said, we see that the peak shifts to smaller wavelengths as the temperature decreases. So as the temperature drops, 7,000 down to 6,000, we see that the peak wavelength is increasing there. So we're doing the opposite there. The peak increases to smaller wavelengths as things get hotter. So it doesn't matter which way you say it, either temperature increases for smaller wavelengths, or as temperature decreases you get larger wavelengths, or temperature decreases as you shift to larger wavelengths. Same thing, just talking about it in different words. Okay? But this drop is really important, this drop here. So as we go hotter and hotter, we get more and more visible light until there's this weird drop off right after. We could keep going into this region here, but then after it would drop off very quickly. Okay, so that's a significant thing. Past peak wavelength, intensity drops rapidly as you go into smaller and smaller wavelengths. Okay, so we know the distribution. Now let's start talking about how to model this. These observations were a real problem. Okay, two scientists, Rayleigh and Jean, we'll see Rayleigh a little bit later on in this unit, tried to model out the relationship between intensity and wavelength using the laws of electromagnetism derived by Maxwell. Okay, now you don't need to know exactly those laws, but you should note that they treated light as a sort of classical wave there, as Maxwell derived, and they got this formula. They got a formula that said intensity should be proportional to the inverse of temperature to the power of 4. Okay, this is mentioned in an exemplar question on, I believe, one of the public exams. So it could be worthwhile keeping that in mind. It's not provided anywhere else though, so maybe just keep that there. They graphed it out, and this dotted line is what they got. And you can see that it's really good down here at the infrared spectrum. You know, it matches up pretty good, but it's quite rubbish here for visual and UV light. And so obviously they missed something. This was called the UV catastrophe, or the UV collapse. Okay? And that's because their model predicted that as you got, didn't matter what, but as you got over to this end, the smaller and smaller wavelengths, that anything that is glowing should give off an near infinite amount of ultraviolet light, which, being Australians, you all know very well, ultraviolet light burns us quite a lot. That's why we get sunburns. Doesn't matter how dark we are, we will get sunburned in light. Some of us are just worse, like me, compared to other people. The being is, when I open my oven, I'm not incinerated in a blast of UV radiation, and they weren't either, because they had ovens. It wasn't like our ovens, but they did have ovens. That's not what happened. So obviously the theory was wrong. Okay, so Jean Rayleigh worked really well down here, but sucked over here. Then we had Wien's model. He did some work, and he came up with a law for the distribution of intensities, which we saw the displacement law that we had before. There's also a distribution law that describes the shape. Now, I've got rid of what the red is here. Let's just say that the red is observed for now. We notice here that red and blue match up really closely here, but then after it gets past peak, it starts to deviate, and then as it gets cooler and cooler, so into lower and lower, so bigger and bigger wavelengths, the blue deviates more and more away from the red. Does it here. So Wien's law here was really good for this ultraviolet and parts of the visible spectrum, but you get to infrared and it sucked. So we had two formula. They worked for different parts, but they couldn't explain why they worked for different parts, and they couldn't make the stupid things work together. Okay, so that's the problem. Okay, Wien good with UV, Rayleigh really great with the infrared, but the two formulas didn't talk to each other, which we don't like in physics. Along came Maxwell Plank. Maxwell Plank was studying temperature and emissivity as part of developing better light bulbs. Okay? They wanted to make sure that the electricity they were putting in and the temperature they were heating the light bulbs up to meant that the light bulbs were effective. They didn't, the good German traditional effectiveness, they didn't want their light bulbs to be wasteful. But he couldn't get his theories, the Rayleigh-Jean theory and Wien's law, to match up with his observed experiments. Because he was sort of working in that, if you think about visible light, he was sort of working in this region here where things don't quite match up. So he went backwards. He created mathematical law from the experimental observations, and one of the things that fell out of it was that energy had to come in fixed quantities, or discrete packets. Discrete meaning, remember, little individual pieces. And he called these quanta, from the word quantity. Okay? The Latin word is quantus, means how much. So if you think quanta, quantity, you're on the right track. So classical theory suggested that energy would be spread out across every possible wave. And as there are more little waves than big waves in a fixed space, we should get lots of small waves which have high frequency, which are the ultraviolet. So you should get a huge amount of UV radiation. But if quantum theory was right, as it is, then light is being given out in fixed pieces, and it's a lot easier to give it out in small pieces with higher wavelengths and lower frequency, and hence lower energy, than it is to give it out as a big piece for a very low wavelength. Okay, now there are some videos I've linked on eLearn that will sort of help explain that. One good analogy I've heard is that you think of energy as or waves as being fussy. They'll have one joule of energy, they'll have 2 joules of energy. They won't have 3, they'll have 4 joules of energy. They won't have 5, 6 or 7, but they'll have 8 joules of energy. Now if I have 7 joules of energy, well, I have to give it out in smaller pieces, a 4, a 2 and a 1. If I have 28 joules of energy, well, I can give out a couple of 8s, but then I've got to give out some smaller stuff as well. But the 8s are a bit tricky. Let's just give them all out in 4s. Okay, so it's a lot easier to give small pieces than it is to give a big piece. You could kind of think it like trying to eat a huge meal. It's a lot easier to cut your meal up into small pieces than it is to shove the whole thing in your mouth in one go. Or it's a lot easier, if you've ever moved a jigsaw, it's a lot easier to sort of break the jigsaw up into some smaller sections, move them, and then put the small sections back together. Okay, so maybe think of energy like a really fussy jigsaw that you've got to move between places. So, that's the story. Now the evidence part. The syllabus requires that you can identify blackbody radiation, provides evidence that electromagnetic radiation is quantized into discrete values. Okay, electromagnetic radiation means light. Quantized means that it's a quantity. Discrete means little individual chunks. And we've talked about what blackbody radiation is in this video. The difference between the prediction of classical theory, okay, the Rayleigh-Jeans theory that we looked at, and the observed reality of blackbody radiation, this is the evidence. So a graph like this, where we have 3,000, 4,000, 5,000 Kelvin, and these are what we see, these 3 lines would be what we observe, and then classical theory over here go, nah, we should do this. The difference between the classical theory and the observed phenomena, that is the evidence. Okay. Now I would go one step further and say, well, this is what the evidence showed, and say that Planck concluded that quantization of energy was required to explain this. Okay, and there's an example question of this that we'll look at in the revision period. So that sort of idea of going, well, this difference, that's the evidence, that's the conclusion it led to. Okay, you only need to identify it, you only need to be able to recall it. Okay, give a sentence or a description. You don't need to explain why. The math is a lot deeper than what we've gone through, but you need to be able to recognize that classical theory, what we actually observed, this difference suggested quantum mechanics. Alright. So in this video we have learnt the following. We've explained blackbody radiation. We've used Wien's law to predict the peak wavelength emitted for different temperature objects. And we've described how the disagreement between classical predictions and experimental evidence provided evidence for the quantization of light. Okay. For your entrance slip to class, please complete questions 1 to 7 in chapter 11.2 Check Your Learning PDF. Copy your answers into the 4.2.7 space on eLearn. Thanks for listening, guys. Have a great night.